Okay, so again, the biggest thing I can stress is just make sure all of your letters are working together. Things we have to be careful of is that our equations are written in the terms of the correct variable, that we are picking where we start and stop our integration in the direction that they are stacking up. So along either your x-axis or your y-axis, and that should match your dx or dy at the end of your integral. Okay, so here is an example of this. A pyramid that is 3 meters high has congruent triangular sides and a square base that is 3 meters on each side. Each cross section of the pyramid, so if I were to slice off the top of the pyramid, each cross section, which you can see highlighted here in this like pink box, and this is going to be key to us, is parallel to the base square, and they are parallel to your x-axis. If you can see that picture, that whatever it's parallel to will tell you what axis you are, or what variable you are integrating with respect to. And it asks us to find the volume of the pyramid. So what they've done is they've turned the pyramid, what we would probably consider on its side, so that it's being measured along your x-axis. Can you see the x-axis running through the middle of your pyramid there? Okay. Because they told us that the pyramid is 3 meters high, we know that it's going to end here on our x-axis at 3, because that's the height of your pyramid. They also told us that the bases of those rectangles are going to be 3 by 3. So what we want to do for ourselves is just visualize any time that we are given a problem like this, what the shape of the cross section is. And in this case, they gave us that our cross section is this little, this is what we're looking at right here, this little square. And I understand that by the time you get to the base that it's going to be a 3 by 3 square, but they're not all 3 by 3, are they? They are, as marked in our picture, some x by x. A square has the same length as it does width. And what you're going to do is visualize that cross section for yourself, and either through the picture or through the information or through the function, which they didn't give us the functions. But we are going to find the area equation for that cross section. So our area then of this one, pretty straightforward, is just x squared. So that's where you're going to start all of these. Just identify for yourself the shape of the cross section and its area. Okay, so then moving over to the side here, our volume will come from the integral. And so when we're doing this, we want to think, okay, which direction is our squares being stacked up? And our squares are being stacked up along our x-axis. Small squares here up to bigger squares this direction. And they start on our x-axis at 0 and they stop at the height of that triangle at 3. And so that's where I get my bounds of integration along our x-axis. We start at 0. We stop at the height of our triangle 3. We fill in our area formula. And hopefully this makes sense that it is volume, because this would be our length times width times height, our change in our x. So it is that volume formula there. So if you guys will please grab your calculators, let's go ahead and just math 9 that. We absolutely could do this one without our calculators, but we got a couple of examples to get through today, so we're going to go ahead and just grab our calculators. Kimmy, what did you get when you did that? Yeah, agreed. Okay. So what did we just find? We just found 9. Here's our units, meters. It's volume, so cubed, right? 9 meters cubed. Questions? Okay. While you guys get this one jotted down, I am going to go to a visualizer here. It says region R is bounded by the relation x squared plus y squared equals 4. You can see that that's that circle that we have in this picture. Is the base of a solid. For this solid, each cross section is perpendicular to the x-axis is a squared. Find the area of the cross section and the volume of the solid. So jot down that example. We will utilize some technology pieces to be able to visualize what's going on. So again, it says we've got this circle, x squared plus y squared equals 4, which means a circle with a radius of 4 centered at the origin, right? That's what we know about that equation. And says for this solid, each cross section is perpendicular to the x-axis and is a square. Find the area of the cross section. So what they're saying is we've got these squares that are stacking up where its base is here. Oh, I froze my screen. Just kidding. Let me try that again. So we've got the base here, and here's your 3D visual of what's going on. Can you see that square there that is got its base in your circle, okay? And what's happening is they're stacking up along, they're creating this solid. So as I pull this along here, so see how the square gets bigger as our diameter, right? Smaller over here, and as I trace this, you can see that it's making a solid as we go along here. And what we're going to do is find the volume of the solid that is created if I put all of those squares out there. Okay, so can you visualize this solid now that you can see? And it's made up of a whole bunch of little squares that get smaller as it gets towards the edge and bigger as we get towards our diameter. Okay, so let's go back to our picture here. A little harder to see when we don't have that, but we got some nice technology pieces, but we've got this square going here. So again, how do we attack this? Well, we know the shape of the cross section. So we're just going to look at the cross section first. And our cross section is a square, but unlike the one we had before, it didn't tell us the length of the side of our square. Sometimes we're going to have to adjust our equation a little bit. So this is the equation x squared plus y squared equals 4. When you're looking at it in this sense, our squares are going to be stacking up this direction because it's perpendicular to our x-axis, which means I need this equation written in terms of y equals x something, right? So if I take that equation and solve for y, we have to be careful on this one because it is plus or minus the square root of 4 minus x squared. We've talked about this before, but when we look at it in terms of just one variable, it actually breaks into the two different parts here. The top part being the positive square root of 4 minus x squared, and the bottom part of the circle being the negative square root of 4 minus x squared. We've had to manipulate it like that before to be able to look at a picture of that in our calculator, right, as two different pieces. So if we look at our cross section here, this part right here that is going from our x-axis up to that top curve would be like 1/2 of the base of our square down here, right? And so as you look at this, that length right there is from our x-axis up to the function is the height there. So this part right here is the square root of 4 minus x squared. But that's only exactly half of the length of the base of your square. So This whole thing would be double that, 2 times the square root of 4 minus x squared. Questions on that? That's probably one of the more challenging parts of this whole section, is when we have to go figure out the dimensions of our cross section. And it's a square, so we know that it's going to be side squared or base times height, or the base and the height are the same thing. So as we go do our area, I can do the side squared formula, or base times height, and our side length is 2 times the square root of 4 minus x squared. Now, I would probably just leave it like that unless I had to hand do the integration part of this, and then I don't really want the radical and the square, like the chain rule thing going on. Please be good algebra students. If you square this, you square the 2 and get 4. You square the square root and just get what's underneath it, right? So it'd be 4 times 4 minus x squared, or 16 minus 4x squared. I don't care which way you write this, but if you're going to simplify it correctly. Okay? Questions so far? Okay, so then volume is just what we did before. Okay, we are stacking up along our x-axis. So look on your x-axis from where that starts to where that stops. It starts here and stops here, and that would be considering the radius of your circle, right? The radius of this circle is actually 2. Agreed? Okay, so it'll start at -2 and end at 2. Fill in your area formula, which we just did the work for down here. I don't care which of those options you pick. And we are integrating across our x-axis, stacking up from left to right. So again, if this goes from left to right, this should be dx. Any questions for me? Okay, grab your calculators and Math 9 that, please. And Spencer, when you got an answer, I'll take that from you. You guys agreeing? Yeah. Okay. I obviously don't have a calculator on me, so. Questions for me so far? Okay. Next one. We're going to deal with this same 2 equations several times. We are going to, for the remainder of this, notice this is A. We're going to change the shape of our cross section a couple different times, but dealing with the same same equation. Notice up there it's kind of written 2 different ways. It says the solid lies between the planes perpendicular to the x-axis at x equals 0 and x equals 4. So we're going to integrate from 0 to 4. The cross sections are perpendicular to the x-axis, and they run from y equals negative square root of x to y equals the square root of x, which can also look like the equation x equals y squared. But since we're integrating with respect to y, they solved this for y by square rooting and got 2 equations, y equals the positive square root of x and y equals the negative square root of x, which would be those 2 different curves there. And the first time it says the cross sections are circular discs with diameters in the xy plane. Write a formula for the area of the cross section. Use it to find the volume of the solid. So we have a visual drawn for us. Perpendicular to the x-axis means we are integrating across our x-axis, and it did say from 0 to 4. Diameter of our circle. Here in our plane, what we have to be careful of is what we need actually for the area formula for a circle. So let's zoom in on just our cross section because we know the shape of it. Cross section is going to be a circle. We need for the area of a circle The radius, right? So what is the radius of our circle? What is the radius of our circle? Yeah, don't overthink this one. Our radius goes here, right? Would start at the center of our circle and go to the edge of our circle, which would be to just one of our functions. Here's this function here, right? So for the circle, all we need is just the radius, which would just be the square root of x, okay? So then our area formula is our radius square root of x squared. Square root of x squared is x. All right, questions so far? Okay, volume. Is our integral from, and it did tell us we're going from, on our x-axis from 0 out to 4. So from 0 to 4 of x pi dx. Now, as you guys are grabbing your calculators and math nining that, I do want to point out one thing, and that is if we are supposed to keep this like in terms of pi or exact, remember that pi is just a constant. You can always pull a constant out front of your integral, right? We can pull a constant multiplier out front. So this actually would be the same as pi times the integral from 0 to 4 of x dx. Why would I ever do that? If I were trying to look at like a multiple choice question that was in terms of pi, I wouldn't type pi into my calculator. I would do the integral from 0 to 4 of x dx and put a pi on the end of it, okay? Let's try that. Just do your integral from 0 to 4 of x dx, and we'll leave this in terms of pi. So we're just typing this in, knowing that we have to multiply our answer by pi. Anna, what did you get for just the integral from 0 to 4 of x dx? And again, we're talking volume, so that would be units cubed. Whatever we just found, I don't know what our units are, but any questions? No? Okay. So like I said, we're going to stick with this same situation, and I'm going to get rid of my picture because they are no longer, oh no, this picture is okay. So same exact equation, x equals y squared or y equals the square root of x and negative square root of x. And this time we're going to look at the cross sections being squares with the base in the xy plane. Okay. So again, we want to zoom in on our cross section and what we need to know about that. So we have two different ways that we can look at this. Because we are integrating along our x-axis, I would instead solve this for y, which we already talked about. It actually gives us two equations. So the bottom part of that curve is y equals the negative square root of x. The top side of that curve is y equals the positive square root of x. Why did I change it to that? Because we're integrating along our x-axis. So I want my equations to say y equals something in terms of x, right? Our cross section, this time in part B, we are changing to the shape of a square. And then just be careful on this. So as we're looking at this, this length right here would be all the way across, and what we know would be here to be the square root of x. Now, here is the mistake a lot of people will say, well, can't I just add those two functions together to get all the way across that and say that it's the square root of x plus the negative square root of x, and now that tells me that the distance across my base is 0? Does that, you see what I'm saying there? If the two different sides are the square root of x and negative square root of x. But as we are talking length across there, remember we are talking a distance. And so we do want it all to be positive. Or understand the mathematical thing that you are doing. The difference between those is you would be subtracting square root of x minus negative square root of x, or ultimately that the entire length of this square's base would be 2 times the square root of x. Very similar to the one we saw earlier. Questions on that? Okay. So our area is our side length squared, 2 square root of x squared, which, just so you can see that again, algebraically simplified, the 2 does get squared. The square root of x squared is x. So we'd end up with 4x. And our volume, we are integrating along our x-axis, starting at 0, moving over to 4. Our area formula, the area of that cross-section is 4x. We are integrating across our x-axis dx. Okay, grab your calculators. Get your calculator out and do these problems, please. Nolan, what'd you get? 32. All right, any questions so far? Okay, again, continuing with the same 2 functions, or 1 function. We are going to switch it up. Now I'm going to get rid of this picture because that is not the correct picture of what's going on here. So we have this function, right? But this time our squares, the diagonal, which is going to be harder for me to draw here, our diagonal is the thing that is running across our plane. And so let me try that again. 3 dimensions is. Where it is our diagonal that is going from our curve to the x-axis in both directions here. So as I look closely at my cross section, what we actually know about this square is the diagonal. And this portion here would be half of our diagonal. Good so far? Is that all? Can we, with my terrible drawing up there, visualize what's going on? So we've shifted how those squares are sitting in our solid, and that it's that diagonal that's running through our x-axis here, which means if we consider this again, y equals the square root of x, this would be the square root of x, or making our diagonal 2 square root of x. Okay. For finding our area of this, need to know what the length of the sides of the square are. How the heck am I supposed to figure that out? Use the triangles. What do we know about those triangles? They are right triangles, and that's kind of a key on this one. Right isosceles triangles, yes. I don't know what its side length is right now, but whatever it is over here is the same over here, right? And so what do we know about the sides of a triangle? What equations work for us on the sides of a triangle? Pythagorean theorem, right? Don't they always have that same relationship? We're not finding the area necessarily of this triangle. We want to know its side lengths. And so we will look at the relationship of the side lengths of a right triangle, and that is your Pythagorean theorem. So I know that a squared plus a squared equals 2 square root of x. And I want to know what a is, or at least what it is in terms of x, right? So using my algebra here, I get that a squared equals the square root of x, or a equals the square root of x. Mia. Oh, it is squared. Pythagorean theorem. Doesn't work well if we don't do the Pythagorean theorem correctly. That's going to look better. Still not pretty. Our side length is going to be square root of 2x. Now we can come back over here and find what we needed. The area of that square, which would be our side length squared. And we just figured out that our side length is square root of 2x, which means our area is 2x. Now we can go do our volume. Again, from the information we had earlier, we're going along our x-axis from 0 to 4. Our area is 2x dx. And Jaden, when you got that typed in, I'll take our volume. Any questions? All right, let's see what the last one is here. Okay, last one is our equilateral triangles. So again, let me get rid of this picture. We got enough time because it's a no TA day. And we have not looked at triangles yet. So let's look at one more example here where we use triangles. Again, you got to be a little bit careful about what part of the triangle we have information about, given our picture here. So it says we've got equilateral triangles with the base in the XY plane. All right, there really will be two different ways you can attack this. First of all, equilateral triangles with its base in the XY plane. Again, that is, we know this much of our triangle will be the square root of x. Because they are equilateral triangles, that means that the full side length would be 2 times the square root of x. Finding the area of this, there really are two different ways you could go about this. If you were like really good at memorizing formulas, there was a formula that you probably learned back in geometry about the area of an equilateral triangle, side squared square root of 3 over 4. If that was like, oh yeah, I know that one, you could actually just put your side length into that formula. Most people, I think, would go to that the area of a triangle is 1/2 base times height, where we would need to figure out from our information what the height is. We don't need to necessarily spend time memorizing some what seems like brand new formula. But if you remember that one, go right ahead and use it. You would not have to find the height of this triangle. Okay. We can find the height of this triangle again using Pythagorean theorem, or if you remember your special right triangles, at this point you actually could do that as well. We are looking at a 30, 60, 90 special right triangle. But again, if you don't remember that, Pythagorean theorem is probably what we would fall back on. Height squared plus square root of x squared equals our hypotenuse squared. So we get our height squared equals 3x, or that our height is the square root of 3x. And then we can do our area formula. 1/2, our entire base is actually 2 square root of x, times our height, which is square root of 3x. I would probably simplify this. First of all, the square root of x and the square root of x is just x. 1/2 times 2 is 1. And we would end up getting x square root of 3. Remember, you do not have to simplify that, right? Because you can just type all of that into your integral. But the area of our cross section is x squared of 3. Now we can go to our volume because we know the area of our cross section. And again, it's the same problem we've been doing. So we're still integrating along our x-axis from 0 to 4. This time with these equilateral triangles that have an area of x squared of 3 dx. Questions for me? And Sarah, when you've got that typed in, I'll take that from you. Any questions? All right. Your assignment tonight is out of the book. Kind of a shorter one because I know these problems take a little bit of time. So draw yourself a picture, draw yourself the cross sections to work into finding the volume. You're on page 410, 1, 3, 5, 6, and then 39 and 41.